Hi, welcome to the video, and in this one we are going to discuss OLS procedure and of course the assumptions which have to be fulfilled in order to enable you apply the OLS procedure. So first of all, let us start with the idea of sample regression line. This should seem familiar to you. Basically, this is a linear function describing relationship between two variables x and y, where x stands for independent variable and y is a dependent variable. So those blue dots stand for actual observations. So you put all the possible values of x on horizontal axis and then you put the data. For instance, for this particular observation, this value of x corresponds to this value of y. And then you design the regression model. And here we have the distance between the actual value of y and predicted value of y. So this is our error term. Of course, it would be nice to design such a regression line which would allow you to predict the value of y with 100% accuracy, but actually this is impossible. You will never achieve this objective. But of course, it would be nice to have a nice fit. And this is the exactly idea behind the ordinary least squares estimator or OLS. So again, for ideal perfect model, we want those error terms to be equal to 0, so there is no difference between the predicted and the actual value of y, but this is impossible. That's why we go for the second best option and we try to minimize those errors. So first of all, we go for squared errors, because we are not interested in the direction, only in magnitude. So it does not really matter for me whether predicted value of y is above the actual value of y or below the actual value of y. It doesn't really matter. So all I want is to make sure that my data is as close to the regression line as possible. And since we have many observations, so there are many error terms, we want to minimize their sum. So that's how we come up with ordinary least squares estimator. Estimator which minimizes the sum of square differences. Okay. So in the remaining part of this video, I would like to discuss the basic assumptions of OLS procedure, and I would like to do this based on some example. So here I collected 1,544 observations in a panel data set, and I am specifically interested in the relationship between income inequality and GDP per capita. So Gini coefficient is used as the measure of income inequality, and higher value of Gini coefficient indicates higher level of income inequality. Here we have the negative coefficient, which means that higher GDP per capita will result in lower value of Gini coefficient and consequently lower level of income inequality, or higher level of income equality, whatever you prefer. Okay, and yeah, here I assumed that model is linear both in variables and parameters. So this is my regression line, and those are actual observations. So the first assumption is linearity in parameters. Your model might be nonlinear in variables, but it has to be linear in parameters, and specifically this means that coefficient has to be linear, like in our example. So this one is pretty easy to ensure. It just depends on your model design. And the second assumption is that there is no dependency between the value of explanatory variable and the error term. So basically we assume that x and u are independent. We measure this dependency by covariance, and if two variables are completely independent, then covariance between them should be equal to 0. So we can check this by plotting residuals versus independent variables on a plot. So actually there is no regression line or whatsoever. It's not enough in order to reject hypothesis about covariance between x and u, but yeah, at least initial data analysis suggests that it is fine. The third assumption states that there should be zero mean value of the stochastic disturbance or the error term. So basically, the expected value of u should be equal to 0. Informally, we expect the positive deviations to cancel out the negative deviations, so there is zero deviation on average. For instance, you can consider the graph on the right-hand side of your screen. So as you can see, we have observations where actual value of y is above the predicted one and below the predicted one. But on average, stochastic deviation is equal to 0. So each positive deviation is equal to the negative one, in terms of magnitude. So on average, stochastic disturbance term is equal to 0. So the next assumption is homoscedasticity. Sounds quite frightening, but actually it means that variance of the error term is independent and constant. And you remember we discussed that variance is the measure of deviation, so we can perform some informal visual analysis. Again, this is my regression line, and those red crosses are actual empirical observations. So as you can see, there is large deviation corresponding to this value, then it starts to decrease. So actually everything is going in this manner, and it's already enough to give you some suspicion about homoscedasticity. Actually, there is some evidence that error term is not homoscedastic but heteroscedastic. Variance is not constant. Later, we will discuss how to figure whether error term is homoscedastic using some formal tests. So at this point, you might just have some idea what it looks like when it is not homoscedastic. The next assumption states that there is no autocorrelation between the disturbance terms. And autocorrelation is when variable is correlated with the value of the same variable in the previous period. So like autocorrelation. So basically, there should be no correlation between the disturbance terms, and autocorrelation is mostly relevant for time series and panel datasets. So we want error terms to be independent. We want them not to be dependent on their values in previous periods. And again, even though we can use some formal tests, we can also do some informal visual analysis. So here on vertical axis, I've got residual, and on horizontal axis, I've got the first leg of the residual. So value of the residual in the previous period, t minus 1. And you can notice some pretty linear fashion, and we can conclude on the presence of positive autocorrelation. So higher value of residual in period t minus 1 leads to the higher value of residual in period t. Finally, we assume that number of observations should be bigger than the number of independent variables. But this assumption is quite easy to fulfill. I mean, basically, it's up to you how many variables to include and how many observations to use. There is nothing to do with nature of the data, so just keep this in mind. But if you even try to run such a regression model, then software will not allow you to do so. So not a big deal. Okay, so finally, if everything is fine, then we actually end up with blue estimator or unbiased and efficient estimator. So we know it is linear, we know it is unbiased, so the expected value of the estimator is equal to the true value of the estimator, and we know it is efficient, which means that variance is minimized. So actually that was it. Thank you for watching and see you in the next video.